Tonight, we're going to explore something that sounds simple, but is actually one of the most mind-bending concepts in all of science. A light year. You've probably heard this term thousands of times. Scientists use it constantly when talking about space. But here's what most people don't realize. When you actually understand what a light year means, when you truly grasp the distance it represents, it changes how you see the universe. It's not just a big number. It's a distance so vast that it challenges our ability to comprehend it. And by the end of this journey, you're going to understand exactly why astronomers need this measurement and why nothing else would work. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's dive in. Let's begin with something familiar: distance. You understand distance in your everyday life. You know how far it is to the grocery store, to your workplace, to the next city over. These are distances you can relate to because you've traveled them. You have a sense of what they mean in terms of time, in terms of effort, in terms of what you'll see along the way. A kilometer is about the distance you can walk in 10 to 12 minutes at a normal pace. These measurements work perfectly well for everyday life. If someone tells you the store is 5 kilometers away, you know roughly how long it'll take to drive there. You can picture the journey in your mind. Maybe you'll pass a few traffic lights. Maybe you'll see some familiar landmarks. The distance is concrete and relatable. If someone says a city is 200 kilometers away, you can plan your trip accordingly. That's about 2 hours of driving. You'll want to fill up your gas tank, maybe bring some snacks. Plan for a rest stop halfway. These distances are human-scaled. They fit into our lives and our experience. We've evolved to understand distances we can walk in a day, distances we can see, distances that matter for survival and navigation. But these measurements start to become awkward when we talk about really large distances. The distance from New York to Los Angeles is about 4,500 kilometers. That's still manageable as a number. It's about a 5-hour flight. People make that journey all the time. They cross the continent. They see the landscape change from East Coast cities to Midwest plains to Rocky Mountains to Southwest deserts and finally to the Pacific coast. The journey is long, but it's achievable. It's within human capability. You can imagine making that trip. The Earth's circumference at the equator is about 40,075 kilometers. That's a big number, but it's still something we can work with conceptually. Early explorers sailed around the world, so we know it's possible to travel that distance, even if it takes months. Ferdinand Magellan's expedition took 3 years to circumnavigate the globe, from 1519 to 1522. Modern commercial flights can circle the Earth in about 45 hours if you could book connecting flights that went all the way around. The Earth is large from our perspective, standing on its surface, but it's not incomprehensibly large. It's a finite thing you could, in theory, explore completely. But now, let's go bigger. The distance from Earth to the Moon is about 384,000 kilometers. This is where normal measurements start to feel inadequate. 384,000 kilometers. That's hard to visualize in any meaningful way. It's not like driving across the country. It's not like sailing around the world. It's something completely different. There's no road to follow, no landmarks to pass, no rest stops along the way. It's just distance, pure distance across empty space. How would you even begin to travel that far? The Apollo astronauts took about 3 days to travel from Earth to the Moon using powerful rockets that accelerated them to speeds of about 11 kilometers per second. That's about 39,600 kilometers per hour, roughly 400 times faster than highway driving. Think about that for a moment. 400 times faster than you've ever driven. And even at that incredible speed, which required some of the most powerful rockets ever built, burning enormous amounts of fuel, it still took 3 days. 3 days of traveling through empty space at speeds no human had ever experienced before, just to reach our nearest celestial neighbor. And that's just to the Moon, the closest celestial body to Earth. The Moon is so close you can see it with your naked eye. You can see details on its surface with a pair of binoculars. It's right there, hanging in the sky. And yet it takes 3 days of rocket travel to reach it. When we start talking about the distance to other planets, to the Sun, to other stars, kilometers become completely useless. The numbers get so large that they lose all meaning. They become abstract symbols on a page rather than distances you can relate to in any way. The distance from Earth to the Sun is about 150 million kilometers. Try to visualize that. You can't, can you? Your brain just sees it as a really big number, but you don't have any intuitive sense of what it means. There's nothing in your daily life that prepares you for a distance like that. Nothing in human evolution prepared us to think about distances this large. We evolved to understand the distance to the next water source, the distance to the hunting grounds, the distance we could walk in a day. We didn't evolve to comprehend 150 million kilometers. The Apollo spacecraft that took astronauts to the Moon traveled at about 11 kilometers per second on average. At that speed, it would take about 160 days, over 5 months, to reach the Sun's distance. The fastest spacecraft humans have ever built, the Parker Solar Probe, travels at speeds up to 192 kilometers per second when it's close to the Sun, using its gravity to slingshot itself to higher and higher speeds. Even at this incredible speed, which is about 17 times faster than the Apollo spacecraft, the probe still takes months to complete its orbits around the Sun. And the star is close. It's right here in our cosmic neighborhood. It's the star we orbit. It's the source of all the light and heat that makes life on Earth possible. We see it every day. It's familiar. And yet it's 150 million kilometers away, a distance so vast that even our fastest spacecraft takes months to traverse it. When we start talking about distances to other stars, even the Sun's distance becomes tiny by comparison. The Sun is our nearest star, and it's 150 million kilometers away. The next nearest star, Proxima Centauri, is about 266,000 times farther than that. 266,000 times farther than a distance that already takes our fastest spacecraft months to cover. This is why astronomers needed a different unit of measurement. Not because they like making things complicated, not because they want to confuse people with big numbers, but because kilometers simply don't work when you're measuring cosmic distances. Using kilometers to measure distances to stars would be like using millimeters to measure the distance between countries. Technically possible, but completely impractical. The numbers become so large, they lose all meaning. They stop being distances and become just numbers, abstract mathematical concepts that don't connect to anything in our experience. So astronomers came up with something different, the light year. But here's what you need to understand right from the start. A light year is not a measure of time. I know it has the word year in it, which makes it sound like time, but it's not. A light year is a measure of distance. It's the distance that light travels in 1 year. Now, why base a measurement on light? Because light is special. Light is the fastest thing in the universe. Nothing can travel faster than light. It's not just a speed limit that we haven't broken yet. It's a fundamental law of physics. The speed of light is a constant, unchanging, the same everywhere in the universe. Whether you're on Earth, on Mars, in another galaxy, or at the edge of the observable universe, light always travels at the same speed. Light travels at about 300,000 kilometers per second. Let me say that again because it's important. 300,000 kilometers per second. Every single second, light travels 300,000 kilometers. This isn't an approximation or an estimate. It's been measured with extraordinary precision. The exact value is 299,792.458 kilometers per second, but for our purposes, 300,000 kilometers per second is close enough. That's incredibly fast. To put it in perspective, light can travel around the Earth's equator about 7.5 times in 1 second. In the time it takes you to snap your fingers, light could circle the entire planet multiple times. In 1 second, light could travel from New York to Los Angeles and back about 37 times. It's a speed that's almost impossible to visualize because nothing in our everyday experience moves anywhere near that fast. The fastest thing most people experience is an airplane. A commercial jet flies at about 900 kilometers per hour, or about 0.25 kilometers per second. Light travels over 1 million times faster than that. The fastest car ever built, the Thrust SSC, reached about 1,200 kilometers per hour, or about 0.33 kilometers per second. Light is about 900,000 times faster. Even the fastest spacecraft we've built, the Parker Solar Probe, at 192 kilometers per second at its peak, is still only about 0.064% the speed of light. It's moving incredibly fast by human standards, but compared to light, it's crawling. When you turn on a light switch, the light reaches your eyes essentially instantly because the room is so small. The light travels from the bulb to your eye in about 10 billionths of a second. That's so fast that there's no perceptible delay. As far as your brain is concerned, the light appears instantly, but the light did travel. It took time. It's just that the time was so short you couldn't possibly notice it. When you see the sun in the sky, you're actually seeing it as it was 8 minutes and 20 seconds ago, because that's how long it takes light to travel from the sun to Earth. The sun is so far away that even light, traveling at 300,000 kilometers per second, needs over 8 minutes to cover the distance. This has an interesting implication. If something happened on the sun right now, if it suddenly changed color, or dimmed, or even exploded, we wouldn't know for over 8 minutes. The event would happen, but the light carrying information about that event would still be traveling toward us. We'd keep seeing the sun as it was, not as it is, for over 8 minutes. When you look at the moon, you're seeing it as it was about 1.3 seconds ago. Not much of a delay, but still a delay. When astronauts walked on the moon and talked to mission control on Earth, every word they spoke took 1.3 seconds to reach Earth, and every response from mission control took 1.3 seconds to reach the moon. This created a nearly 3-second gap in every exchange. You can hear this delay in the recordings. There's always this pause, this lag, because the radio signals carrying their voices traveled at the speed of light, and even light needs time to cross the distance between Earth and the moon. Light doesn't travel instantly. It has a speed, and that speed, while incredibly fast, is still finite. This is one of the most important discoveries in physics. Before the late 1600s, most people assumed light traveled instantly. You opened your eyes and you saw things immediately, so it seemed like light must be instantaneous. But in 1676, a Danish astronomer named Ole Rømer made a careful observation of Jupiter's moons and noticed something strange. The times when the moons disappeared behind Jupiter varied depending on where Earth was in its orbit. When Earth was closer to Jupiter, the eclipses happened earlier than predicted. When Earth was farther from Jupiter, they happened later. Rømer realized this was because light took time to travel the different distances. He calculated that light took about 22 minutes to cross the diameter of Earth's orbit. His calculation wasn't quite right because he didn't know the exact size of Earth's orbit, but he proved that light has a finite speed. Today, we know the speed of light with extraordinary precision, We've measured it using lasers, atomic clocks, and sophisticated equipment. We've confirmed that it's constant, that it doesn't change depending on how fast you're moving or where you are. And we've discovered that this speed, this constant, is woven into the very fabric of the universe. It's not just the speed that light happens to travel at, it's a fundamental property of space-time itself. So a light year is the distance light travels in 1 year at this speed. Let's calculate that. Light travels at 300,000 kilometers per second. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365 days in a year. If we multiply all of these together, 300,000 times 60 times 60 times 24 times 365, we get approximately 9.46 trillion kilometers. To be more precise, it's 9,460,730,472,580.8 kilometers. But for simplicity, we usually just say 9.46 trillion kilometers. That's what a light year is. 9.46 trillion kilometers. Not a measure of time, but a measure of distance. The distance that light, the fastest thing in the universe, travels in 1 year. And that's the number we're going to try to understand tonight. Because understanding what a light year means is essential to understanding our place in the universe, the distances between stars, and the true scale of the cosmos. But first, we need to talk about what a trillion actually means, because most people have no intuitive sense of how large this number really is. We throw around words like million, billion, and trillion in everyday conversation. We hear about government budgets in the trillions, about billionaires, about millions of people, but we don't really understand the massive differences between these numbers. They all sound like big numbers, so we treat them as roughly equivalent. But they're not. The differences between them are staggering. A million is 1,000 thousands. If you saved $1 every day, starting today and continuing without ever stopping, you'd have $1 million in about 2,740 years. That's a long time, but it's conceivable. You can imagine a timeline stretching back 2,740 years. That takes you back to ancient Greece, to the early Roman Republic, to a time when humans were already building cities, writing books, creating civilizations. It's a comprehensible span of time. A billion is 1,000 millions. Now we're jumping up by a factor of 1,000. If you saved $1 every second, not every day, but every single second, you'd need about 32 years to save $1 billion. That's more than the time it takes for a generation to grow up. If you started counting seconds when you were born and counted continuously without sleeping, eating, or taking any breaks whatsoever, you'd be 32 years old when you reached 1 billion. Think about that. 1 million seconds is about 11.5 days. That's conceivable. You can imagine a period of 11.5 days. It's less than 2 weeks. But 1 billion seconds? That's 32 years. The jump from 1 million to 1 billion is enormous. A trillion is 1,000 billions. And here's where numbers start to completely lose their connection to anything we can relate to. If you counted to 1 trillion, counting one number per second without stopping, it would take you about 31,700 years. Let me put that in perspective. That's longer than all of recorded human history. Agriculture, the foundation of civilization, was only invented about 10,000 years ago. Before that, all humans lived as hunter-gatherers, moving from place to place, following animal herds and seasonal plants. Writing systems appeared about 5,000 years ago in Mesopotamia. The pyramids of Egypt were built about 4,600 years ago. The wheel was probably invented about 5,500 years ago. To count to 1 trillion, you'd need to have started counting before any of that happened. You'd need to have started when humans still lived in small tribal groups. when there were no cities, no nations, no written language, no agriculture, no permanent settlements. You'd need to have been counting through the entire span of human civilization, through every invention, every discovery, every empire that rose and fell, through every war, every peace, every triumph and tragedy in human history. And you'd still be counting today, and you'd still have thousands of years to go before you reached 1 trillion. Let me try to make this even more concrete. 31,700 years ago, modern humans were living in the last ice age. We were using stone tools. We were hunting woolly mammoths and giant ground sloths. We had barely begun to spread across the globe. Modern humans had only recently left Africa and were just starting to populate Europe and Asia. There was no language as we know it today, no art beyond the most primitive cave paintings, no technology beyond sharp rocks and wooden spears. That's how far back 1 trillion seconds takes you. And a light year is 9.46 trillion kilometers. Every single one of those kilometers is a kilometer. It's not an abstract unit. It's a real distance, the distance you could walk in about 10 to 12 minutes at a normal pace. And there are 9.46 trillion of those individual kilometers in one light year. 9.46 trillion separate, distinct kilometer-long segments, each one the length of a walk to your local store. So when we say a light year is 9.46 trillion kilometers, we're talking about a distance that dwarfs anything in our daily experience. You can write it down, you can calculate with it. You can use it in equations. But grasping it intuitively is nearly impossible. Our brains simply didn't evolve to handle numbers this large. We evolved to count the number of people in our tribe, the number of animals in a herd, the number of days until the seasons change. We can count to a few hundred, maybe a few thousand if we really concentrate. But 9.46 trillion, that's so far beyond our cognitive capabilities that it might as well be infinity. The best way to understand a light year is to build up to it gradually, starting with distances we can comprehend and scaling up step by step. We're going to take this journey slowly, moving from the familiar to the unfamiliar, watching as distances that seem vast become tiny compared to what comes next. Let's start with 1 light second, 300,000 kilometers. That's about the distance from Earth to the Moon and 3/4 of the way back. Think about what that means. Light leaves Earth, travels all the way to the Moon, which is 384,000 kilometers away, bounces back, and gets about 3/4 of the way to Earth, and all of that happens in 1 second. 1 single second. When astronauts on the Moon talked to Mission Control in Houston during the Apollo missions, there was a communication delay of about 1.3 seconds each way. The astronauts would say something, and Mission Control wouldn't hear it for 1.3 seconds because the radio signal, traveling at the speed of light, needed that long to make the journey. When Mission Control replied, their response took another 1.3 seconds to reach the Moon, so every exchange had a nearly 3-second delay built in. It's subtle when you listen to the recordings, but it's always there. There's this pause, this lag, because of the distance the signals had to travel, and because nothing, not even radio waves, can travel faster than light. 1 light minute is 60 light seconds, 18 million kilometers. The Sun is about 8 light minutes away from Earth, which is about 150 million kilometers. So 1 light minute is roughly 12% of the distance from Earth to the Sunday. If you could somehow stand on the Sun, which you obviously can't because it's a ball of plasma with a surface temperature of about 5,500 degrees Celsius, but if you could somehow stand there and look at Earth, you'd be seeing Earth as it was 8 minutes and 20 seconds ago. If Earth suddenly exploded, you wouldn't know for over 8 minutes. The event would happen, but the light from that event, carrying the information about it, would take over 8 minutes to cross the distance between Earth and the Sun. This has practical implications for space exploration that most people don't think about. When NASA operates rovers on Mars, there's always a communication delay because Mars is so far away. At its closest, when Earth and Mars are on the same side of the Sun in their orbits, Mars is about 32 million kilometers from Earth, which is about 2 light minutes. At its farthest, when Earth and Mars are on opposite sides of the Sun, the distance is about 400 million kilometers, about 22 light minutes. This means, when the Perseverance rover is operating on Mars, every command sent from Earth takes between 2 and 22 minutes to arrive, depending on where Mars is in its orbit. And any data the rover sends back takes the same amount of time to reach Earth. You can't drive a rover on Mars in real time like you'd drive a remote-controlled car on Earth. The delay is too long. Instead, NASA engineers have to plan the rover's activities carefully. They analyze images from previous days, plan a route, write a sequence of commands, send those commands to Mars, and then wait. If something goes wrong, if the rover gets stuck on a rock or encounters an obstacle, they can't react instantly. They have to wait for the information to reach Earth, which takes anywhere from 2 to 22 minutes. Then, they have to analyze what went wrong, figure out a solution, write new commands, send those commands, and wait another 2 to 22 minutes for them to arrive. A problem that might take seconds to solve with a remote-controlled car on Earth can take an hour or more to solve on Mars. 1 light hour is 60 light minutes. That's about 1,080 million kilometers. Over 1 billion kilometers, that's a distance so vast that even imagining it is difficult. The planet Saturn, at its closest approach to Earth, is about 1.2 light hours away. Saturn is one of the most distant planets you can see with the naked eye from Earth, a beautiful ringed world that's been observed since ancient times, and it's about 1.2 light hours away. When the Cassini spacecraft was orbiting Saturn from 2004 to 2017, taking incredible close-up photographs of the planet and its moons, there was over an hour of delay between when it took a picture and when that picture reached Earth. The spacecraft would take a photo, convert it to digital data, transmit it as a radio signal traveling at the speed of light, and over an hour later, scientists on Earth would receive it. This meant that Cassini couldn't be controlled in real time. Engineers and scientists couldn't watch what the spacecraft was seeing and adjust its path on the fly like you might steer a car or pilot a drone. Instead, they had to program entire sequences of commands days or weeks in advance, upload them to the spacecraft, and trust that Cassini would execute them correctly. If something went wrong, the spacecraft had to be smart enough to handle it autonomously, to recognize the problem and switch to a safe mode, because by the time the problem was reported back to Earth and new commands were sent, over 2 hours would have passed. The situation could have changed completely in that time. 1 light day is 24 light hours, about 25,900 million kilometers. We're now talking about distances where even our fastest spacecraft become incredibly slow by comparison. Voyager 1, the spacecraft that launched in 1977 and is currently the most distant human-made object from Earth, is about 24 light hours away as of 2025. It's been traveling for nearly 50 years, moving at about 17 kilometers per second, which is about 61,200 kilometers per hour. That's incredibly fast by any human standard. At that speed, you could travel from one side of the United States to the other in about 2 minutes. And yet, after nearly 5 decades of constant travel through the vacuum of space with nothing to slow it down, Voyager still hasn't traveled 1 full light day from Earth. This is roughly the distance to the heliopause, the boundary where the Sun's influence ends and interstellar space begins. The heliopause is where the solar wind, The constant stream of charged particles flowing out from the Sun in all directions finally slows down and mingles with the interstellar medium, the thin gas that fills the space between stars. Voyager 1 crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. It was a historic moment, a milestone in human exploration. But it's still within one light day of the Sun. It's still, in cosmic terms, right here in our neighborhood. 1 light week is 7 light days, about 181 billion kilometers. Now we're in a region where nothing human-made has ever been, and nothing will be for decades or centuries to come. This is deep space, far beyond the planets, far beyond anything we've directly explored. Out here, the Sun would no longer appear as the overwhelming source of light and heat it is from Earth. It would appear as just a bright star, brighter than other stars certainly, but just a point of light in the darkness. If you were somehow out here, floating in space at 1 light week from the Sun, you'd see the Sun as a brilliant star, but you'd also see thousands of other stars scattered across the black sky. You'd realize, perhaps for the first time, that the Sun is just one star among many. 1 light month is roughly 30 light days, about 778 billion kilometers. At this distance, if you looked back at the Sun through a telescope, you'd see it as just another star, not much brighter than many others in the sky. The solar system, with all its planets and moons and asteroids and comets, would be barely visible. Even with a powerful telescope, you might see Jupiter as a faint dot, but the inner planets would be lost in the Sun's glare. Everything we think of as the solar system, all the planets we've studied and sent spacecraft to, all the worlds we know, would be compressed into a tiny region around an ordinary star. And 1 light year is 365 light days. It's 12 light months. It's 52 light weeks. It's 8,760 light hours. It's 525,600 light minutes. It's 31,536,000 light seconds. See how quickly the numbers scale up? We started with 1 light second, which was already an enormous distance by human standards, about the distance from Earth to the Moon and most of the way back. And we've been multiplying by larger and larger numbers, 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 7 days in a week, 30 days in a month, 12 months in a year, and we're just now getting to 1 light year. 9.46 trillion kilometers. That's the distance light travels in 1 year, moving at 300,000 kilometers every single second for 365 days straight. And this is the fundamental unit astronomers use to measure the distances between stars, because stars are separated by distances measured in light years, and nothing smaller makes sense when you're dealing with these vast cosmic scales. So why do astronomers use light years? Because every other option is worse. Imagine if astronomers used kilometers for everything. Proxima Centauri is about 40,140 billion kilometers away. That's awkward, hard to remember, and doesn't give you any intuitive sense of the distance. But if I tell you Proxima Centauri is 4.24 light years away, that's cleaner. You can compare it to other distances. If one star is 4 light years away and another is 40 light years away, you immediately know the second is 10 times farther. Light years also connect distance and time usefully. When you look at a star 4 light years away, you're seeing light that left 4 years ago. You're looking into the past. This connection becomes crucial when studying the universe. The speed of light is not just fast. It's the speed limit of the universe. Nothing can go faster. And this isn't a technological limitation that we might overcome with better engineering or more powerful rockets. It's a fundamental law of physics built into the very structure of space-time itself. The speed of light isn't just a speed. It's a cosmic constant that defines the relationship between space, time, energy, and matter. Einstein's theory of special relativity, published in 1905, showed that as objects approach the speed of light, strange things happen. These aren't just theoretical predictions. They're observed facts, confirmed by countless experiments over the past century. Time slows down for the moving object relative to stationary observers. This is called time dilation, and it's been measured directly. The object's mass effectively increases, or more precisely, its inertia increases. It becomes harder and harder to accelerate. The amount of energy required to accelerate it increases without limit as you approach light speed. To actually reach the speed of light would require infinite energy, which is impossible. The universe doesn't contain infinite energy. Therefore, nothing with mass can reach the speed of light. Let me explain why this happens. In our everyday experience, if you're on a train moving at 50 kilometers per hour and you throw a ball forward at 20 kilometers per hour relative to the train, someone standing on the ground would see the ball moving at 70 kilometers per hour. The speeds add. This seems obvious and it works perfectly well for everyday speeds. But Einstein showed that this simple addition doesn't work when you're dealing with speeds close to the speed of light. If you're on a spacecraft moving at half the speed of light and you shine a flashlight forward, you might think the light would move at 1.5 times the speed of light, at least from the perspective of someone watching you. But it doesn't. The light still moves at exactly the speed of light, 300,000 kilometers per second, both from your perspective on the spacecraft and from the perspective of someone watching you from outside. This seems impossible. How can the light be moving at the same speed for both observers when one observer is already moving at half the speed of light? The answer is that space and time adjust to keep the speed of light constant. If you're moving very fast, time literally runs slower for you from the perspective of a stationary observer. And distances in the direction you're moving actually contract. These aren't optical illusions or measurement errors. They're real physical effects. Time and space are not absolute. They're relative depending on your motion. The only thing that's absolute, that's the same for everyone regardless of how they're moving, is the speed of light. This has been tested experimentally countless times. Particles in particle accelerators move at speeds very close to the speed of light. We can measure how long they live before decaying. And we find that particles moving at 99.9% of the speed of light live much longer than identical particles at rest. Time is literally moving slower for them. This isn't theory. It's measured fact. GPS satellites orbiting Earth move fast enough and are far enough from Earth's gravitational field that time dilation becomes measurable. The atomic clocks on GPS satellites run at a slightly different rate than identical clocks on the ground. If GPS didn't account for this time dilation effect, your GPS navigation would be off by several kilometers within just a few hours. The fact that GPS works is proof that time dilation is real. Cosmic rays, high-energy particles from space, create muons when they hit the upper atmosphere. Muons are subatomic particles that decay very quickly, with a half-life of about 2 microseconds. At this rate, even moving at close to the speed of light, muons created in the upper atmosphere shouldn't be able to reach the ground before decaying. And yet, we detect muons at ground level all the time. Why? Because from our perspective, the muons are moving so fast that time dilation extends their lifetime. What's 2 microseconds from the muon's perspective becomes much longer from our perspective, long enough for them to reach the ground. Only massless particles, like photons, which are particles of light, can travel at the speed of light. Photons have no rest mass, so they don't need infinite energy to reach light speed. In fact, photons must always travel at light speed. They can't slow down or speed up, From the moment they're created to the moment they're absorbed, they travel at exactly the speed of light, no faster, no slower. This is simply what photons do. It's their nature. This has profound implications for space travel that go beyond just engineering challenges. Even if we developed perfect propulsion systems with access to unlimited energy, even if we solved every engineering problem imaginable, we still couldn't travel faster than light. The 4.24 light-years to Proxima Centauri represents a minimum travel time of 4.24 years, even in the most optimistic scenario where we could somehow accelerate a spacecraft to nearly the speed of light. And that's just getting to the nearest star. Most destinations in space are much, much farther away. Some science fiction proposes ways around this limitation. Warp drives that bend space around a spacecraft, allowing it to effectively travel faster than light without actually moving faster than light through space. Wormholes that create shortcuts through space-time, connecting distant points in space. Hyperspace, an alternate dimension where the laws of physics are different and faster than light travel is possible. These are creative ideas, and some, like warp drives, have a basis in theoretical physics. The Alcubierre drive, proposed in 1994, is a theoretical solution to Einstein's field equations that would allow faster-than-light travel by contracting space in front of a spacecraft and expanding it behind. But there are problems. The Alcubierre drive would require exotic matter with negative energy density to work. No such matter is known to exist. Some physicists think it might be impossible on fundamental grounds. Even if exotic matter exists, you'd need an enormous amount of it, possibly more mass energy than exists in the entire observable universe. And there are causality problems. If you could travel faster than light, you could potentially travel backward in time, creating paradoxes. Wormholes, if they exist, would likely be incredibly unstable and would collapse before anything could pass through them. Keeping a wormhole open long enough to travel through it might require more energy than exists in the entire universe. And again, there are causality problems. If wormholes allow faster-than-light travel, they also allow time travel to the past, with all the associated paradoxes. Hyperspace is pure speculation with no basis in known physics. It's a science fiction concept that makes for good stories but doesn't have any connection to real physics or mathematics. There's no evidence that any such thing exists or could exist. As far as we know, based on over a century of careful experiments and observations, the speed of light is an absolute barrier. It's not a challenge to be overcome with better technology. It's a fundamental law of nature. When we talk about stars that are hundreds or thousands of light years away, we're talking about distances that might be fundamentally unreachable with any technology that's consistent with the laws of physics as we understand them. The light year doesn't just measure distance, it measures a barrier, a limit, a boundary beyond which the normal rules of cause and effect start to break down. Let's talk about Proxima Centauri because it's our closest stellar neighbor and helps us understand these distances practically. Understanding Proxima Centauri, the closest star beyond our Sun, gives us a sense of what it means when we say even the nearest stars are impossibly far away. Proxima Centauri is a small red dwarf star in the Alpha Centauri system, which is actually a triple star system. Two of them, Alpha Centauri A and B, are Sun-like stars orbiting each other. They're similar in size and brightness to our Sun, and they orbit their common center of mass every 79.9 years in a slow gravitational dance that's been going on for billions of years. If you could see them up close, Alpha Centauri A and B would look like two suns circling each other against the darkness of space. Proxima Centauri is much smaller, about 1/8 the Sun's mass and 1/7 its diameter. It's so small and dim that you can't see it with the naked eye, even though it's our nearest stellar neighbor. You need a telescope to spot it. Red dwarfs like Proxima Centauri are the most common type of star in the galaxy, making up about 70% of all stars. But they're all so dim that none of them are visible to the naked eye despite being relatively common. When you look up at the night sky, every star you can see with your naked eye is either larger and brighter than the Sun, or it's not a star at all, but a planet. Proxima Centauri is 4.24 light-years away, about 40,140 billion kilometers. That's 40 with 12 zeros after it. To put this in perspective, if you could somehow travel at the speed of the fastest spacecraft humans have ever built, the Parker Solar Probe at 192 kilometers per second, it would take you about 6,800 years to reach Proxima Centauri. That's longer than all of recorded human history. Writing was invented about 5,000 years ago. You could have started your journey when humans first learned to write, traveled continuously at the fastest speed any human spacecraft has ever achieved, and you'd still be traveling today, still thousands of years away from your destination. There have been proposals for faster spacecraft. The Breakthrough Starshot initiative, announced in 2016 by physicist Stephen Hawking and entrepreneur Yuri Milner, proposes using powerful ground-based lasers to accelerate tiny spacecraft to about 20% of light speed. The concept is elegant and scientifically sound, at least in principle. You build a spacecraft that's essentially a computer chip with a camera weighing maybe a gram attached to an ultra-thin light sail made of reflective material, perhaps only a few atoms thick. Then you point massive arrays of lasers at it from Earth. The laser light pushes on the sail, and because the spacecraft is so incredibly light, it can be accelerated to tremendous speeds. At 20% of light speed, which is about 60,000 kilometers per second, a probe could reach Proxima Centauri in about 20 years. Add another 4 years for signals to travel back to Earth at light speed, and you could potentially get data from Proxima Centauri in 24 years from launch. That's within a human lifetime, which is exciting. You could launch a mission when you're young and potentially see the results before you die. But the engineering challenges are enormous, perhaps insurmountable with current or near-future technology. First, you need incredibly powerful lasers. The proposal calls for a laser array with a total power of about 100 gigawatts. That's roughly the output of 100 nuclear power plants, all focused into a laser beam a few kilometers wide. This beam would need to track the tiny spacecraft as it accelerates, keeping the light precisely focused on the sail. Any deviation, and the sail would drift out of the beam and the acceleration would stop, leaving the spacecraft coasting at whatever speed it had reached. Second, the spacecraft needs to survive the journey. At 20% of light speed, you're moving at 60,000 kilometers per second. At this speed, collisions with even tiny particles become catastrophic. A speck of dust, something smaller than a grain of sand, hitting the spacecraft at this speed would release energy equivalent to a large bomb. The spacecraft would need shielding to protect it, but any shielding adds weight, and weight is the enemy when you're trying to accelerate something with light pressure. The more the spacecraft weighs, the more power you need to accelerate it, and the equation gets worse and worse as you add weight. Third, you need to be able to communicate with the spacecraft over 4 light-years of distance. The tiny probe would need a laser or radio transmitter powerful enough to send data back to Earth from 4.24 light-years away. At that distance, any signal spreads out enormously. The power needed to send a detectable signal is substantial, and you have to fit this capability into a spacecraft the size of a computer chip. It's like trying to shout across an ocean and be heard clearly on the other side. Fourth, You need to actually hit Proxima Centauri's star system and fly past it at the right distance and angle to get useful data. At 20% of light speed, the spacecraft is traveling so fast that it crosses the orbit of Mars in about 40 minutes. The entire width of our solar system, from the Sun to Neptune, is crossed in about 6 hours. You get one shot. There's no slowing down, no course corrections once you're up to speed, because slowing down would require just as much energy as speeding up, and you don't have that energy available in a spacecraft weighing a gram. The spacecraft flies past Proxima Centauri at 60,000 kilometers per second, has maybe a few hours or at most a few days when it's close enough to take useful pictures and measurements, and then continues on into the void, never to be seen again, drifting through interstellar space forever. So while breakthrough Starshot is an interesting concept, and it's based on real physics rather than science fiction, it remains highly theoretical. The technology doesn't exist yet, and there are formidable challenges that might be impossible to overcome. Even if we somehow built such a craft and successfully sent it tomorrow, it would be at least 20 years before it reached Proxima Centauri, and another 4 years before we got any data back. That's a 24-year round trip for information, assuming everything works perfectly, which in the history of space exploration has never been a safe assumption. And this is just to reach our nearest stellar neighbor, the closest star to our Sun. With technology we can actually build today, the kind of spacecraft we know how to engineer and launch with current rockets and current materials and current computer systems, getting to Proxima Centauri would take not decades, but millennia. We'd need to build multi-generational spacecraft, massive vessels that could support human crews for thousands of years. The people who arrived at Proxima Centauri would be the distant descendants of those who launched, perhaps hundreds of generations removed, living in a world they'd never left, traveling to a destination they'd only heard about in stories passed down through the centuries. When you look up at the night sky, you're seeing stars at various distances, and you're seeing them as they were years or even centuries ago. This is one of the most profound implications of the light year. Distance and time become inseparable. You cannot separate where something is from when you're seeing it. Light travels at a finite speed. It's incredibly fast, but it's not instantaneous. When light leaves a star and travels through space toward Earth, that journey takes time. And during that time, things can change. The star might change brightness. It might change color. It might explode. By the time the light reaches your eyes, the star you're seeing might be completely different from how it is right now, or it might not even exist anymore. Sirius, the brightest star in the night sky, is 8.6 light-years away. When you look at Sirius tonight, you're seeing light that left that star 8.6 years ago. You're seeing Sirius as it was when you were 8.6 years younger. If you're 20 years old, you're seeing Sirius as it was when you were about 11, probably in middle school. If you're 40, you're seeing it as it was when you were in your early 30s. The Sirius you see tonight is Sirius from the past, not Sirius as it exists right now in this present moment. Now, Sirius is a stable main sequence star. It's not going to change much over a few years or even a few decades. In 8.6 years, Sirius doesn't age noticeably. Stars change very slowly from a human perspective, over millions or billions of years rather than years or decades. But the principle is what matters here. You're not seeing Sirius as it is. You're seeing Sirius as it was. You're looking back in time every time you look at a star. Vega is another bright star, about 25 light-years away. If you're 25 years old and you look at Vega tonight, you're seeing light that left that star the year you were born. When that light began its journey toward Earth, you hadn't been born yet. You didn't exist. Your parents might have been looking up at that same star, seeing light that left Vega 25 years before that, 50 years ago total. The Vega you see tonight is a younger Vega, showing you what that star looked like a quarter century ago, not as it is right now. Beetlejuice, the red supergiant in the constellation Orion, is about 550 light-years away. It's one of the most famous stars in the night sky, easily visible as the bright reddish star marking Orion's shoulder. The light you see from Beetlejuice tonight started its journey toward Earth in the year 1474 during the Italian Renaissance, before Columbus sailed to the Americas, when Leonardo da Vinci was 22 years old and Michelangelo was about to be born. In 1474, the Byzantine Empire had fallen to the Ottoman Turks 21 years earlier. The printing press had been invented only about 20 years before. Most of Europe was still emerging from the Middle Ages. The modern world, as we know it, didn't exist yet, and the light from Betelgeuse that you see tonight started its journey back then. It's been traveling through space for over 500 years, crossing the vast darkness between Betelgeuse and Earth to arrive at your eye tonight. Betelgeuse is a particularly interesting example because it's a massive star nearing the end of its life. Stars like Betelgeuse don't last as long as smaller stars like the Sunday. They burn their fuel much faster. At some point in the relatively near future, astronomically speaking, within the next 100,000 years or so, Betelgeuse will explode as a supernova. When it does, it will briefly shine as bright as the full moon in our sky, visible even during the day. It will be a spectacular event, one of the most dramatic astronomical events visible from Earth in human history. But here's the thing, Betelgeuse might have already exploded. The explosion might have happened centuries ago. Maybe it happened in the years 1600 or 1700 or 1800, but we wouldn't know yet. We wouldn't have any way of knowing. The light from that explosion would still be traveling toward us through space, moving at the speed of light, taking 550 years to make the journey. So if Betelgeuse exploded in the year 1700, we won't see it until about the year 2250. The star could already be gone right now, destroyed in a catastrophic supernova explosion, and we'd still see it shining peacefully in the sky for centuries to come, completely unaware that we're seeing a ghost, an image of something that no longer exists. Polaris, the North Star, is about 445 light-years away. When its current light began traveling toward us, the first permanent English colonies in North America hadn't been established yet. Jamestown wouldn't be founded for another 12 years. The Pilgrims wouldn't arrive at Plymouth Rock for another 26 years. William Shakespeare had just begun writing his plays. He'd written some of his early works, but hadn't yet written Hamlet, Macbeth, King Lear, or most of his other famous plays. The United States wouldn't exist for another 180 years. When that light from Polaris began its journey, the world was fundamentally different from today. And tonight, that ancient light enters your eye. You're connected across space and time by photons that have been traveling for 4.5 centuries. Within about 20 light-years of Earth, there are about 130 known star systems. Some are single stars, like our Sun. Others are binary systems with 2 stars orbiting each other, or even triple star systems like Alpha Centauri. Understanding this stellar neighborhood helps us appreciate both the distances involved and the variety of stars that exist in our cosmic backyard. Barnard's star is the second closest star system to Earth after Alpha Centauri, about 6 light-years away. It's a red dwarf, much smaller and dimmer than the Sun. What makes Barnard's star particularly interesting is that it's moving toward us relatively quickly by stellar standards. It has the largest proper motion of any known star, meaning it moves across the sky faster than any other star as seen from Earth. Over the course of decades and centuries, we can actually see Barnard's star change position relative to other stars. In about 10,000 years, it will be closer to Earth than Proxima Centauri is now, becoming our new nearest stellar neighbor. But even at its closest approach, it will still be nearly 4 light-years away. The distances between stars are so vast that even when stars are moving toward each other, it takes thousands or tens of thousands of years for that motion to make a noticeable difference in the distance between them. Wolf 359, about 7.9 light-years away, is one of the fastest-moving stars relative to the Sun, traveling at about 119 kilometers per second. That's fast by stellar standards. Most stars in our region of the galaxy move at speeds of a few tens of kilometers per second relative to each other. Wolf 359 is moving much faster. Yet even at this speed, it's moving at only about 0.04% of the speed of light. Stars move, but they move slowly compared to the vast distances between them. Even the fastest-moving nearby star would take tens of thousands of years to travel a light-year. Sirius, 8.6 light-years away, is actually a binary system with 2 stars orbiting each other. Sirius A is a bright, white main-sequence star about twice the mass of the Sun. It's the brightest star in our night sky, partly because it's relatively close and partly because it's intrinsically quite luminous. Sirius B is completely different. It's a white dwarf, the dense remnant of a star that exhausted its nuclear fuel and collapsed. White dwarfs are fascinating objects. They're about the size of Earth, but have the mass of a star. Sirius B has about the mass of our Sun compressed into a sphere about the size of our planet. This makes it incredibly dense. A teaspoon of material from Sirius B would weigh about 5 tons on Earth. The 2 stars orbit each other every 50 years, locked together by gravity, each following an elliptical path around their common center of mass. The Milky Way is a spiral galaxy containing between 100 billion and 400 billion stars. That's a huge range because it's actually quite difficult to count stars in our own galaxy. We're inside it, like trying to count trees while standing in the middle of a forest. Dust blocks our view in many directions. Dim stars are hard to detect. And the galaxy is so large that we can't see all of it at once from our position. But the best estimates suggest somewhere between 100 billion and 400 billion stars, with the most likely number being around 200 to 300 billion. Our Sun is just one of these stars, an ordinary yellow dwarf star of average size and brightness. There's nothing special about our Sun from a galactic perspective. It's not the biggest, not the brightest, not the hottest, not the coolest. It's just a typical star, one among hundreds of billions. And it's located in one of the spiral arms, about 26,000 light-years from the galactic center. 26,000 light-years. The light we see from the center of our galaxy, if we could see through all the dust blocking the view, left the galactic center 26,000 years ago. When that light began its journey, humans were still living as hunter-gatherers in the Stone Age. Agriculture hadn't been invented yet. There were no permanent settlements, no cities, no civilization as we understand it. People lived in small nomadic bands, following animal herds, gathering wild plants, using simple stone tools. Writing wouldn't be invented for another 21,000 years. Everything we think of as human civilization, everything from the first farms to the first cities to the first writing to all the ancient empires to the modern world, all of it has happened while light from the galactic center was traveling toward us. And that light, which left when humans were still primitive hunter-gatherers, arrives at Earth tonight. The Milky Way is roughly 100,000 light-years across from one edge of the spiral arms to the other. If you could somehow travel at the speed of light, which you can't, it would take you 100,000 years to cross the galaxy from one side to the other. 100,000 years. Modern humans, Homo sapiens, are about 300,000 years old as a species. So you could have started crossing the galaxy when the first modern humans appeared in Africa, traveled at the speed of light for 100,000 years. And you'd only be 1/3 of the way across the galaxy today. The Sun orbits the galactic center at a speed of about 230 kilometers per second. That sounds fast, and it is fast. At that speed, you could travel across the United States in about 3 minutes. You could circle Earth in just under 3 minutes. But even at this incredible speed, it takes the Sun about 225 million to 250 million years to complete one orbit around the galaxy. The last time the Sun was in its current position in the galaxy, dinosaurs were just beginning to evolve on Earth. The first dinosaurs appeared about 230 million years ago. Since then, the dinosaurs evolved, ruled Earth for over 160 million years, went extinct 66 million years ago, mammals took over, and humans eventually evolved. And the Sun has only just now returned to approximately the same position in the galaxy where it was when dinosaurs first appeared. One of the most exciting developments in astronomy over the past few decades has been the discovery of exoplanets, planets orbiting stars other than our Sun. Until 1992, we knew of only one planetary system, our own solar system, with its 8 planets orbiting the Sun. We suspected other stars might have planets, but we had no direct evidence. Then, in 1992, astronomers detected the first planets orbiting another star, a pulsar. In 1995, they found the first exoplanet orbiting a normal Sun-like star. And since then, the discoveries have exploded. As of 2024, we've confirmed the existence of over 5,000 exoplanets, with thousands more candidates waiting to be verified. The TRAPPIST-1 system, about 40 light-years away, contains 7 Earth-sized planets orbiting a small red dwarf star. 3 of these planets are in the habitable zone, where temperatures could potentially allow liquid water to exist on the surface. This discovery, announced in 2017, was revolutionary for several reasons. It showed that small red dwarf stars can host multiple rocky planets. Since red dwarfs are the most common type of star in the galaxy, making up about 70% of all stars, this suggests rocky planets might be extremely common throughout the universe. The TRAPPIST-1 system is also remarkable because the planets are packed tightly together. All 7 planets orbit closer to their star than Mercury orbits our Sun. But because the star is so small and cool, 3 of the planets receive about the same amount of energy from their star as Earth receives from the Sun. If you stood on one of these planets, you'd see the other planets in the sky, some appearing larger than our Moon appears from Earth. The planets are so close together that travel between them would be far easier than travel between planets in our solar system. When we observe the TRAPPIST-1 system today, we're seeing it as it was 40 years ago in 1985. If there's intelligent life on one of those planets, and if that life developed radio technology and started broadcasting signals into space, those signals would take 40 years to reach us. We'd be receiving signals today that were broadcast in 1985. And if we detected such a signal today and sent a response, it would take another 40 years for our response to reach them. They'd receive our reply in 2065. That's an 80-year round trip for a single exchange of information. You could ask a question and die of old age before receiving an answer. Let's think about what communication means when distances are measured in light years. This is one of the most challenging and sobering aspects of the scale of space, and it has profound implications for any future where humanity might try to establish settlements on other worlds or make contact with alien civilizations. Radio waves travel at the speed of light. They're electromagnetic radiation, just like visible light but with longer wavelengths. When we send radio signals into space, they propagate outward in all directions at 300,000 kilometers per second. But even at this incredible speed, the fastest speed possible in the universe, communication across light years takes years. Voyager 1, our most distant spacecraft, is now about 24 light hours away from Earth. That means there's a communication delay of about 24 hours each way. When mission controllers on Earth send a command to Voyager, that command takes about 24 hours to reach the spacecraft. The radio signal travels at light speed, covering about 25 billion kilometers to reach Voyager. Any data Voyager sends back takes another 24 hours to reach Earth. There's roughly a 48-hour delay for any two-way communication. If something goes wrong with the spacecraft, if a system fails or an anomaly occurs, Voyager must handle it autonomously. By the time engineers on Earth know there's a problem and send new commands to address it, 2 full days have passed. The situation could have changed completely in that time. The New Horizons spacecraft, which flew past Pluto in July 2015, was about 4.5 light hours away from Earth during the flyby. All the data it collected during those few precious hours near Pluto had to be stored on board the spacecraft, then transmitted back to Earth over the following months. Every command sequence had to be programmed weeks or months in advance. Mission controllers couldn't react to what the spacecraft was seeing in real time. They had to plan everything perfectly, anticipate every possible scenario, and trust that the spacecraft would execute its mission autonomously. Now imagine trying to establish communication with a human settlement on a planet orbiting Proxima Centauri, 4.24 light-years away. You send a message asking how things are going, how the crops are growing, whether there are any problems that need addressing. That message travels at light speed for 4.24 years. 4 years, 2 months, and about 20 days later, your message arrives. If they respond immediately, writing their response and sending it right back, their answer takes another 4.24 years to reach you. That's over 8 years for a single exchange of information. You could ask about their latest harvest and receive an answer about crops that were eaten 4 years ago. You could ask how a sick person is doing and receive news of their death years after it happened. You could send advice or help, but by the time it arrives, the situation will have changed completely. Any kind of real-time communication, the kind of immediate back-and-forth conversation we take for granted, is completely impossible across these distances. Conversations would be painfully, frustratingly slow. Debates would span decades. A diplomatic negotiation between Earth and a Proxima colony could take a century or more to resolve, with each party having to carefully consider their responses, knowing that years would pass before hearing back, and years more before their reply could be answered. This has profound implications for governance and society that go far beyond just inconvenience. A colony 4 light-years away couldn't be governed from Earth in any meaningful sense. Any laws or directives sent from Earth would arrive years out of date. The political situation on Earth could change completely between when a message was sent and when it arrived. By the time the colony receives orders from Earth, those orders might be obsolete, overturned by new governments or new policies. The colony would need to be autonomous, capable of making its own decisions on everything from resource allocation to conflict resolution to emergency response, because waiting years for approval or guidance on every decision would be impossible. The colony and Earth would drift apart culturally over time, developing their own customs, their own ways of life, their own solutions to problems. They'd be connected by messages from the past, letters from another time, but unable to maintain the kind of immediate, ongoing connection that holds societies together. Over generations, they might become so different that they'd barely recognize each other anymore. They'd share a common origin, a common history up to the point of separation, but from that point forward, they diverge, evolving separately like species isolated on different islands. For more distant stars, it gets even worse. A settlement 10 light-years away would have a 20-year round-trip communication time. Messages you send to your children living there would reach them when they're adults, possibly with children of their own. Their responses would return when your grandchildren are grown, when you're old or possibly dead. You'd exchange letters across the decades like messages from different eras. You could share news and stay in touch in some abstract sense, but you couldn't have a relationship in any normal meaning of the word. A civilization 100 light-years away would have a 200-year communication delay. You could send a message and neither you, nor your children, nor your grandchildren, nor even your great-grandchildren would live to see the reply. Only your great-great-great-great-grandchildren, living in a world you could barely imagine, might hear back from the distant civilization. The conversation would span generations. Each generation sending messages to strangers they'd never meet, people separated not just by distance but by time, receiving messages from people long dead. If you could travel close to light speed, something strange happens with time. This is Einstein's time dilation, and it's been confirmed by countless experiments. It's not speculation or theory in the sense of being unproven. It's observed fact, as solidly established as gravity or electromagnetism. As you approach light speed, time slows down for you relative to stationary observers. The faster you go, the more extreme this becomes. This isn't just clocks running slow. This is time itself passing more slowly. Your heartbeat, your thoughts, your aging, your metabolism, everything happens more slowly from the perspective of someone who's not moving with you. Though from your perspective, sitting in your spacecraft, everything seems normal. Time passes normally for you. It's everyone else's time that seems to be passing quickly. Imagine a spacecraft that could somehow reach 99.9% of light speed. Not quite light speed, but very close. You board this spacecraft and travel to a star 10 light-years away, then turn around and come back. From Earth's perspective, this journey takes about 20 years. 10.1 years to get there at 99.9% of light speed, and another 10.1 years to come back. Anyone watching from Earth would see your spacecraft take about 20 years for the round trip. But because of time dilation, you would age much less. At 99.9% of light speed, time passes about 22 times slower for you than for people on Earth. So while 20 years passed on Earth, you would only experience an age about 11 months. You'd step off the spacecraft having aged less than a year, while everyone you knew aged 20 years. Your younger sibling might now be older than you. Your children, if you had any, might now be adults older than you. You've traveled into their future. If you traveled even faster, at 99.99% of light speed, you could travel to a star 100 light-years away and back. From Earth's perspective, this journey takes over 200 years. But from your perspective, due to extreme time dilation at this speed, the journey might take only a few years of your life. You'd experience a few years of travel time, living through a few years aboard the spacecraft. But when you return to Earth, over 200 years would have passed. Everyone you knew would be long dead. The world would be completely different. Political systems would have changed. Technologies would have advanced. Languages might have evolved. You'd return to a future Earth that would be as foreign to you as if you'd traveled forward in time. Let's zoom out even further. The observable universe is the region of space from which light has had time to reach us since the Big Bang. The universe is about 13.8 billion years old. Light has been traveling toward us for all that time. But the observable universe is larger than 13.8 billion light-years because the universe has been expanding while the light was traveling toward us. The observable universe is about 46.5 billion light-years in radius, making it about 93 billion light-years across. This is the distance to the edge of what we can possibly see. Beyond this distance, space has been expanding so fast that light from those regions hasn't reached us yet and never will. There's a cosmic horizon beyond which we cannot see, not because we don't have powerful enough telescopes, but because the light simply hasn't had time to reach us yet, given the age of the universe and the rate of expansion. Within this observable universe are an estimated 2 trillion galaxies. Each galaxy contains billions or trillions of stars. If you multiply it out, the total number of stars in the observable universe is estimated at around 200 billion trillion. That's a 2 followed by 23 zeros. And we know from observations that most stars have at least one planet orbiting them. So there are probably similar numbers of planets, maybe even more. The universe is filled with worlds, more worlds than we could ever count, more worlds than we could ever visit, even if we had unlimited time and unlimited technology. At the largest scales, the universe has structure. Galaxies aren't randomly scattered through space like grains of sand. They're organized into clusters, groups of galaxies held together by gravity. These clusters are organized into superclusters, massive structures containing multiple galaxy clusters. And the superclusters are arranged in filaments, enormous thread-like structures stretching hundreds of millions of light-years across space. Between these filaments are vast voids, regions with very few galaxies, empty spaces that can be hundreds of millions of light-years across. The universe is expanding, space itself is stretching, carrying galaxies with it like raisins in rising bread dough. This isn't just galaxies moving through space. Space itself is expanding, creating more space between distant objects. For nearby objects, this expansion is negligible, overwhelmed by other forces. The space between Earth and the Moon isn't expanding in any meaningful way. Gravity holds Earth and Moon together. The space within our solar system isn't expanding. Gravity holds the planets in their orbits. The space within our galaxy isn't expanding. Gravity holds the stars together in the Milky Way. But on larger scales, between galaxies and especially between galaxy clusters, separated by hundreds of millions or billions of light years, the expansion becomes significant and eventually dominant. Distant galaxies are receding from us as space expands between us and them. The farther away a galaxy is, the faster it's receding. This isn't because the galaxies themselves are moving through space at high speeds. They're sitting relatively still in their local regions of space. But the space between us and them is expanding, and the cumulative expansion over vast distances adds up to high recession speeds. For galaxies that are far enough away, space between us and them is expanding faster than light can travel through it. This doesn't violate the cosmic speed limit because the galaxies themselves aren't moving faster than light through space. They're essentially stationary in their local space. But the space itself is expanding so rapidly that the distance between us grows faster than light could traverse it. It's like trying to walk on a treadmill that's moving backward faster than you can walk forward. You're walking at your normal speed, but you're moving backward relative to your starting point because the treadmill is moving faster than your walking speed. This means there are regions of the universe that are moving away from us so fast that light from those regions will never reach us, ever. Not in a billion years, not in a trillion years, not ever. There's a cosmic horizon beyond which we cannot see, not because the light hasn't had time to reach us yet, but because it never will reach us. The expansion of space is carrying those regions away faster than light can close the gap. We are fundamentally, irreversibly cut off from those regions of the universe. Given the vast number of stars and planets, given that the universe is 13.8 billion years old, given that life arose on Earth relatively quickly after conditions became suitable, It seems likely that life should exist elsewhere, perhaps even intelligent, technological life. And yet we've never detected any signs of alien civilizations. No radio signals carrying messages or even just the electromagnetic noise of alien technology. No laser pulses, no megastructures. No signs of large-scale engineering projects. Nothing. The universe appears to be silent. This is called the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The light year might be part of the answer. The distances between stars are so vast that they present enormous, perhaps insurmountable barriers to communication and travel. Our radio signals, our television broadcasts, our radar installations have been leaking into space for about a century now. These signals travel at light speed, spreading outward in an expanding sphere. They've now reached all stars within about 100 light-years of Earth. That sounds like a lot. 100 light-years is a huge distance by human standards. But the Milky Way galaxy is 100,000 light-years across. Our signals have covered a sphere 100 light-years in radius, in a galaxy 100,000 light-years across. That's a tiny fraction of the galaxy. We've barely announced our presence to our immediate cosmic neighborhood. And even those signals are getting weaker as they spread out. The farther they travel, the more they disperse, spreading out over a larger and larger sphere. By the time our TV broadcasts reach a star a few dozen light-years away, they're so faint they'd be almost impossible to detect above the background noise of space, even with very sensitive equipment. Any alien civilization trying to detect us would need extremely powerful radio telescopes pointed in our exact direction at the right frequency at the right time to pick up our signals. So what does all this mean for us? How should we think about light years in our daily lives? For most people, light years don't affect daily life at all. You don't need to think about Proxima Centauri being 4.24 light years away when you're deciding what to have for breakfast, whether to take an umbrella or which route to take to work. But there's value in occasionally stepping back and contemplating these scales. It provides perspective on our place in the universe. When you realize that Earth is a small planet orbiting an ordinary star and that the nearest other star is over 4 light-years away and that our galaxy contains hundreds of billions of stars and that there are trillions of galaxies in the observable universe, it changes how you see things. Your problems, whatever they are, exist on a tiny planet in a vast universe. That argument with a friend, that stress at work, that anxiety about the future, that disappointment, that frustration, all of it happens on one small world. The nearest star doesn't care about your problems. The galaxy doesn't notice. The universe continues its slow evolution completely indifferent to human affairs. This isn't meant to diminish your experiences or suggest your problems don't matter. Your life matters to you, and that's what's important. Pain is pain. Joy is joy. Love is love. These things are real and important, regardless of the scale of the universe. But sometimes, when things feel overwhelming, when you're stressed or anxious or worried, it can help to remember the scale of the universe. It can help to remember that you're living on a small planet orbiting an ordinary star in a vast cosmos, and that from that cosmic perspective, your problems are temporary, local, small. Not unimportant, but small, contained, manageable. There's also something beautiful about understanding light years. When you look up at the night sky, you're not just seeing points of light. You're seeing stars that are light years away. You're seeing photons that have been traveling through space for years or centuries to reach your eyes. You're connected to those distant suns across vast distances of space and time. You're part of the universe, made of atoms forged in stars, looking up at other stars, understanding your place in the cosmic order. Every star has a story. Some are young, just forming from collapsing clouds of gas and dust, beginning their lives as nuclear furnaces. Some are middle-aged like our Sun, steadily burning hydrogen in their cores, stable and long-lived. Some are old, approaching the end of their lives, having exhausted their fuel, destined to become white dwarfs, cooling slowly over trillions of years, or to explode as supernovae, scattering their atoms across space to be recycled into new stars and planets. And all of them are separated by light years, by distances so vast that even light needs years to cross them. The universe is a sparse place, with tiny islands of light separated by enormous oceans of darkness. And yet those islands are connected by light, connected by gravity, connected by the fact that they're all made of the same stuff. Atoms forged in the hearts of earlier stars, scattered and recycled and reformed into new generations of stars and planets and potentially life. As our technology improves, our ability to measure distances in light years becomes more precise. The Gaia spacecraft is creating the most precise three-dimensional map of our galaxy ever made. It's measuring positions and distances of over 1 billion stars. Future telescopes will allow us to see even farther. James Webb is already detecting galaxies over 13 billion light-years away. Future observatories might see even farther back, closer to the Big Bang. We're also discovering more exoplanets every year. As of 2024, we've confirmed over 5,000 exoplanets with thousands more candidates. Many are dozens or hundreds of light-years away. We're mapping what exists at these vast distances. In the future, we might send robotic probes to nearby stars. Breakthrough Starshot proposes sending tiny spacecraft to Proxima Centauri. Even if successful, probes would take over 4 years to send back data. But barring revolutionary breakthroughs in physics, light years will remain a fundamental barrier. The distances between stars are vast, and light speed is finite. This isn't a problem to be solved. It's a fundamental property of the universe we live in. Understanding light years changes how we see our place in the universe, and it raises profound questions about the future of humanity and our relationship with the cosmos. These aren't just abstract philosophical questions. They have real implications for how we think about space exploration, the search for life, and the long-term future of our species. For most of human history, the universe was small. Ancient people thought the stars were lights attached to a celestial sphere just beyond the moon and planets. The entire cosmos was contained within a space you could reach if you climbed high enough. Even when we realized the stars were distant suns, we had no sense of how distant they truly were. A few million kilometers? A few billion? The numbers were beyond our ability to measure, so they remained abstract, undefined. It wasn't until the early 20th century that we began to accurately measure the distances to stars and realize just how vast space truly is. When Harlow Shapley calculated the size of the Milky Way in 1918, showing it was about 100,000 light-years across, many astronomers were shocked. The universe was far larger than anyone had imagined. And when Edwin Hubble showed in 1929 that the spiral nebulae were actually distant galaxies millions of light-years away, the universe suddenly expanded again by orders of magnitude. We went from thinking the Milky Way was the entire universe to realizing it was just one galaxy among potentially billions. Today, we know the observable universe is 93 billion light-years across and contains about 2 trillion galaxies. That's a number so large, it's almost meaningless. But it represents a real physical space that exists all around us. Every direction you look, if you could see far enough, you'd see galaxies stretching away into the distance, more and more galaxies, until finally you'd reach the edge of the observable universe where the light simply hasn't had time to reach us yet. This knowledge changes our perspective in fundamental ways. We're not at the center of the universe. We're not special in any cosmic sense. We live on a typical planet orbiting a typical star in a typical galaxy in a typical region of space. There's nothing unique about our location. If you were transported to another galaxy billions of light years away, you'd see a similar view, galaxies in every direction stretching away to the horizon. The universe looks roughly the same from every vantage point. This is both humbling and empowering. Humbling because it shows how insignificant we are in cosmic terms. The entire history of human civilization, everything we've ever done, every war fought, every empire built, every discovery made, all of it has happened on one small planet, in one small corner of one typical galaxy. From a cosmic perspective, we barely register. We're like bacteria living in a drop of water, completely unaware of the ocean that surrounds us. But it's also empowering because it shows what we're capable of. We figured this out, we measured these distances, we understood our place in the cosmos. We built telescopes and spacecraft and mathematical models that allowed us to see and measure things billions of light years away. We're tiny, but we're also incredibly capable. We're conscious beings who can understand the universe that created us. That's remarkable. Understanding light years forces us to confront difficult truths about space exploration and the future of humanity beyond Earth. The distances involved are so vast that they might represent fundamental barriers that no amount of technological advancement can overcome. Consider what it would take to send humans to another star. Proxima Centauri is 4.24 light-years away. With current technology, the fastest spacecraft we've built travels at about 192 kilometers per second at its peak. At that speed, it would take about 6,800 years to reach Proxima Centauri. That's longer than all of recorded human history. You could have launched your mission when humans first invented writing, and it still wouldn't have arrived yet. To make interstellar travel practical, we'd need to go much faster. Even at 10% of light speed, which would require revolutionary new propulsion systems far beyond anything we can currently build, it would still take over 42 years to reach Proxima Centauri. That's longer than most careers, longer than the typical span from graduation to retirement. And that's just to reach the nearest star. Most stars are much farther away. The engineering challenges are formidable. You need enormous amounts of energy to accelerate a spacecraft to these speeds. You need to protect the crew from radiation during the journey. You need to provide life support for decades. You need to deal with the psychological effects of being confined in a small spacecraft for most of your life, never seeing Earth again, traveling through empty space toward a destination you might not reach in your lifetime. Multigenerational ships have been proposed, massive vessels that could support hundreds or thousands of people for the centuries it would take to reach another star. The people who arrive would be the distant descendants of those who launched. They'd have been born on the ship, lived their entire lives on the ship, and would finally arrive at a destination they'd only heard about in stories. The ship would effectively be a small, moving civilization, cut off from Earth, evolving its own culture and society during the long voyage. But even multi-generational ships might not be practical. How do you maintain a closed ecosystem for centuries? How do you prevent genetic problems from inbreeding in a small population? How do you ensure the descendants still want to complete the mission their ancestors started? What if they decide, several generations in, that they want to turn around and go home? What if there's a disaster, a system failure, a plague that wipes out most of the population? There's no rescue coming. They're light years from help. Some have proposed suspended animation or cryogenic freezing, putting the crew to sleep for the journey and waking them when they arrive. This would solve many problems. No need for decades of life support, no psychological issues from long confinement, no generational drift in mission objectives. But we don't know if such technology is even possible. Can human bodies survive being frozen for decades or centuries and then revived? What about cellular damage from ice crystal formation? What about the effects on the brain and memory? These are all unsolved problems that might not have solutions. The reality is that interstellar travel with humans aboard might simply be impractical given the constraints imposed by the speed of light and the vast distances measured in light years. We might be confined to our own solar system for the foreseeable future, perhaps permanently. That doesn't mean we can't explore other star systems with robotic probes, but human exploration of other stars might remain forever in the realm of science fiction. The light year also shapes our thinking about the possibility of contact with alien civilizations. If intelligent life exists elsewhere in the universe, and many scientists think it probably does given the vast number of stars and planets, the distances measured in light years might make contact impossible even if both civilizations survive for millions of years. Let's say there's an advanced technological civilization on a planet orbiting a star 50 light-years away. They've developed radio technology and have been broadcasting signals into space for a century, just like we have. Those signals are now passing through our region of space, but they're incredibly faint after traveling 50 light-years, spreading out over an enormous sphere. To detect them, we'd need to be pointing very sensitive radio telescopes in exactly the right direction, at exactly the right frequency, at exactly the right time. The chances of that happening by accident are incredibly small. Even if we did detect their signals, think about what happens next. We'd be receiving signals they broadcast 50 years ago. If we responded immediately, our response would take another 50 years to reach them. That's a 100-year round trip for a single exchange. You could ask a question and die of old age before receiving an answer. Your grandchildren might hear the response to a question you asked. This fundamentally changes the nature of any potential contact. There can be no dialogue in any normal sense, no conversation, no negotiation in real time. Instead, it would be more like an exchange of encyclopedia entries. Each civilization sends everything they know, everything about their history and science and culture, and hopes the other civilization receives it and responds similarly. It would be more like archaeology than communication, studying the records left by a distant civilization, records that are decades or centuries old by the time they arrive. And that assumes both civilizations survive long enough and remain interested in communication long enough for this exchange to happen. Humans have only been broadcasting radio signals for about a century. We don't know if we'll still be broadcasting in another century, let alone several centuries. Civilizations might rise and fall on timescales shorter than the light travel time between stars. We might detect signals from a civilization that went extinct centuries ago, listening to the radio echoes of a dead world. There's also the disturbing possibility that the universe might be full of civilizations, but they're all so far apart that none of them ever make contact. The average distance between intelligent civilizations might be thousands of light years. At such distances, even detecting each other becomes nearly impossible, and communication becomes pointless. Each civilization develops alone, makes its discoveries alone, asks its questions alone, and eventually dies alone, never knowing if anyone else was out there. One of the most profound implications of understanding light years is the realization of just how isolated we are. The distances between stars are so vast that meaningful contact or travel might simply be impossible, leaving civilizations forever isolated in their own small regions of space. Even within our own galaxy, even assuming there are millions of technological civilizations, the average distance between them might be thousands of light years. At such distances, communication becomes almost pointless. By the time you receive a message and send a response, thousands of years have passed. The civilization that sent the original message might not even exist anymore. Their planet might have been destroyed by an asteroid impact, or they might have destroyed themselves in a war, or their star might have become unstable and rendered their world uninhabitable. You'd be sending a message to ghosts. This creates a picture of a universe that might be full of life, perhaps even intelligent life, but where that life is forever isolated by the vast distances of space. Each civilization develops alone, asks its questions alone, makes its discoveries alone, and eventually dies alone, never knowing if anyone else was out there, never making contact with other minds under other suns. There's something melancholy about this. We've evolved as social creatures. Connection with others is fundamental to who we are as humans. We build communities, share knowledge, collaborate on projects. The idea of being alone in the universe, or of being surrounded by others but forever unable to reach them or communicate with them meaningfully, is profoundly isolating. But there's also something beautiful about it. It means every civilization that does arise is precious. If we're alone, or effectively alone because we can't reach anyone else, then we carry a unique responsibility. We're the universe's way of knowing itself in this particular corner of space. The thoughts we think, the art we create, the science we discover, the love we feel, all of it is unique to us. We're not just one civilization among millions. We might be the only minds in our region of space, the only consciousness for dozens or hundreds of light years in any direction. This makes what we do matter more, not less. Every act of kindness, every discovery, every work of art, every moment of joy or connection or understanding, it all matters because it's happening here and now and might not be happening anywhere else nearby. We're alone, but we're also important. We're small, but we're also precious. We're insignificant in cosmic terms, but we're also irreplaceable because there might not be anyone else like us for light years in any direction. Tonight, we've explored the light year in depth. We've looked at what it means, how it's measured, what distances it represents, and its implications for understanding the universe. We've taken a journey from the familiar scales of our everyday life to the almost incomprehensible scales of cosmic distance. A light year is 9.46 trillion kilometers. The distance light travels in 1 year, moving at 300,000 kilometers per second. It's the unit astronomers use because kilometers and other terrestrial units of measurement become completely unwieldy when dealing with cosmic distances. When you're measuring distances to stars and galaxies, you need a unit that's large enough to make the numbers manageable while still being based on something physical and measurable. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. That's the closest stellar neighbor we have, and it's still so far away that with current technology, it would take thousands of years to reach it. Our galaxy, the Milky Way, is roughly 100,000 light-years across from one edge to the other. To cross our own galaxy at the speed of light, you'd need 100,000 years. The observable universe is 93 billion light-years across, containing an estimated 2 trillion galaxies, each with billions or trillions of stars. When you look at stars in the night sky, you're not seeing them as they are right now. You're seeing light that has traveled for years or centuries or even millennia to reach your eyes. You're literally looking into the past. Sirius, the brightest star in the night sky, is 8.6 light-years away. You're seeing it as it was 8.6 years ago. Beetlejuice, the red supergiant in Orion, is about 550 light-years away. You're seeing it as it was during the Renaissance, over 5 centuries ago. A light year connects distance and time in a fundamental way, showing that they're unified aspects of space-time rather than separate concepts. The speed of light is a fundamental speed limit built into the structure of the universe. Nothing can travel faster than light. This isn't a technological limitation that we might overcome with better engineering. It's a law of physics, a consequence of how space-time works. This means that distances measured in light-years represent real barriers to communication and travel. Stars that are light years away are separated from us not just by space, but by time. Even traveling at the speed of light, which is impossible for anything with mass, you'd still need years to reach nearby stars and thousands or millions of years to reach distant galaxies. The universe is expanding, and that expansion is accelerating. Dark energy, a mysterious force we don't understand, is pushing the universe apart at an ever-increasing rate. Distant galaxies are receding from us as space expands between us and them. In the far future, billions of years from now, the universe will be much emptier from our perspective as more and more galaxies are pushed beyond our cosmic horizon, carried away by the expansion of space faster than their light can reach us. Despite these vast distances and fundamental barriers, despite the isolation imposed by the light year, we've learned an enormous amount about the universe. We've mapped billions of stars, measuring their distances with ever-increasing precision. We've detected thousands of exoplanets orbiting other stars, some of them potentially habitable. We've observed galaxies billions of light years away, seeing them as they were in the early universe shortly after the Big Bang. The light year has been our fundamental tool for measuring and understanding these cosmic distances, for mapping the universe and our place within it. Let's end where we began. A light year is the distance light travels in 1 year, 9.46 trillion kilometers. A number so large it challenges our ability to comprehend it, a distance so vast it makes our planet seem infinitesimally small by comparison. But you don't need to fully comprehend it intuitively to appreciate what it represents. You can appreciate that the universe is vast beyond our ability to fully grasp. You can appreciate that light from distant stars has been traveling for years, decades, centuries, or even millennia to reach your eyes tonight. You can appreciate that we live in a tiny corner of an enormous cosmos, on a small planet orbiting an ordinary star in one galaxy among trillions. There's something profoundly humbling about understanding light years and the distances they represent. It reminds us how small we are in the grand scheme of things, how brief our individual lives are compared to cosmic timescales, how isolated we are in space, separated from even our nearest stellar neighbors by distances that would take thousands of years to cross with any technology we can currently build. It puts our concerns and worries and problems into perspective, showing us that from a cosmic viewpoint, the things that seem so important in our daily lives are temporary and local. But there's also something empowering about this knowledge. We figured this out. Despite being small creatures on a small planet, we measured these vast distances. We understood our place in the universe. We built telescopes and spacecraft and developed mathematical frameworks that allowed us to see and comprehend things billions of light years away. We're tiny, confined to one small world for now, but we're also remarkably capable. We're conscious beings who can understand the universe that created us, who can look up at the night sky and comprehend what we're seeing, who can contemplate distances measured in trillions of kilometers and time spans measured in billions of years. From a cosmic perspective, you're insignificant. Your life is a brief flicker, lasting perhaps 80 or 90 years if you're lucky, in a universe that's 13.8 billion years old and will continue for trillions of years more. You exist for the blink of an eye on a tiny planet orbiting an ordinary star. But you're also remarkable in your own way. You're made of atoms forged in the hearts of stars that died billions of years ago, their matter scattered across space and eventually recycled into new stars and planets, and ultimately into you. You're literally made of stardust, the product of cosmic processes that have been operating for billions of years. You're a way for the universe to know itself, to understand itself, to appreciate its own vastness and beauty and complexity. So the next time you look up at the stars on a clear night, remember what you've learned tonight. Those points of light scattered across the darkness are not just lights. They're distant suns, massive balls of fusing hydrogen, each one potentially hosting its own system of planets and moons. They're light years away, separated from us by distances so vast that the light entering your eye right now, the photons that traveled across space to reach you, has been traveling for years or centuries. Some of that light began its journey before you were born. Some of it left its star before your grandparents were born. You're connected to those distant stars across the vast distances of space and time, linked by light that has crossed the cosmic void to reach you. The universe is large beyond comprehension. You are small, a single person on a single planet. But you're here, and you can understand, at least conceptually, if not intuitively, what a light year really means. You can grasp that the universe is measured in these vast units, that space is filled with distances that dwarf anything in human experience. And that understanding, that ability to comprehend your place in the cosmos, is extraordinary. It's what makes us human, what separates us from other life on Earth. We can look up and understand what we're seeing. We can contemplate infinity and our own smallness simultaneously. We can feel both humbled and empowered by the same knowledge. And perhaps that's the most important thing to take away from understanding light years. Not just the technical definition, not just the mathematics of 9.46 trillion kilometers, but what it means for us as a species, for our future, for our place in the cosmos. We stand at a unique moment in history. We're the first generation of humans to truly understand the scale of the universe. Our ancestors looked up at the same stars, wondered about the same questions, but they didn't have the tools or knowledge to measure the answers. They couldn't know that the stars were distant suns. They couldn't know that those suns were light years away. They couldn't comprehend the vast distances that separate us from the rest of the universe. But we can. We've measured these distances. We've calculated them precisely. We know that Proxima Centauri is 4.24 light-years away. We know that the Andromeda Galaxy is 2.5 million light-years distant. We know that the observable universe stretches 93 billion light-years across space. These aren't guesses or estimates, they're measurements, backed by decades of careful observation and calculation. This knowledge changes us, it has to. When you truly understand that the nearest star would take thousands of years to reach with our current technology, when you grasp that the light from distant galaxies has been traveling for billions of years to reach your eyes, when you comprehend that we might be fundamentally isolated by the vast distances of space, it shifts your perspective on everything. It makes our differences seem smaller. The things we argue about, the borders we draw, the conflicts we engage in, all of it happens on one tiny planet in a vast cosmos. We're all together on this small world, separated from our nearest stellar neighbors by distances measured in light years. From that perspective, the things that divide us seem less important than the things we share. It also makes our existence seem more precious. If we're alone, or effectively alone because we can't reach anyone else across the light years that separate us, then what we do here matters enormously. We might be the only consciousness in our region of space. The only minds that can contemplate the universe and understand what they're seeing. The only beings who can create art, discover scientific truths, feel love and compassion and wonder. That's a profound responsibility. It means we need to take care of this planet, this tiny island of life in the cosmic ocean. It means we need to preserve and protect the knowledge we've gained, the understanding we've developed. It means we need to think long-term, not just about the next year or decade, but about the next century, the next millennium, the long future of humanity among the stars. The light year is more than just a unit of measurement. It's a reminder of our place in the universe. A reminder that we're part of something vastly larger than ourselves, but also that we're unique and precious within that vastness. A reminder that the stars are both incredibly far away and intimately connected to us through the light that bridges the cosmic distances. Every time you look up at the night sky, you're participating in something ancient and profound. You're seeing across light years. You're looking back in time. You're witnessing the universe in all its glory. And you're part of that universe, made of the same atoms, following the same physical laws, connected by the same fundamental forces that govern everything from the smallest particle to the largest galaxy cluster. That's what a light year really means. Not just distance, but connection. Not just isolation, but belonging. Not just our smallness, but our significance within that smallness. Thank you for joining me on this journey through space and time. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep explorations of the cosmos. And remember, even though light years represent distances almost beyond comprehension, they're also what connect us to the stars. Every time you look up at the night sky, you're seeing across light years. You're seeing the universe. And the universe, vast as it is yours to explore. Good night, and may you never look at the stars the same way again.